Photographic images are often as important a component of office documents as text and graphics. The level of support that computers give for computer graphics has increased substantially in the last few years, as has the degree of computer graphic package integration with the operating system. This has made it much easier for people to develop new graphical applications because they don't need to start from scratch anymore. In addition to new applications, new user interfaces are being developed for existing systems in order to make things easier for the novice user. The support for photographic material has not reached the same level of sophistication though. Typically, the level of support for this kind of data is much more primitive, slow, expensive and resource intensive, with protocols that are not so clearly defined. If the level of support for photographic material could be raised to the same level as graphics material, a whole range of new applications and modes of interaction would emerge. One can think of many examples where easy manipulation of photographic material would be of great benefit, particularly in the areas of design and planning. For example, in landscape design, you could visualize your garden with the plants at various stages of maturity, or see the effect of moving plants, shrubs and trees from place to place. In house design, proposed modifications to existing structures could be shown that can provide a much better indication of the result than, for example, an architectural plan. This might be particularly valuable in communicating design ideas to planners, zoning officials, or your neighbours. In the same vein, it's possible to experiment with interior design in places where colour, texture and detail can make all the difference. You could see the total effect of changing colour or design, or of adding different styles of furniture. Some people might find it more entertaining to experiment with their own appearance. Certainly doing it this way would be faster, less risky, less expensive and more amusing. Clearly, there are at least as many opportunities for this technology as there are for photography itself. There are several systems on the market already that digitally manipulate photographs. They have several disadvantages. For example, some of the best cost millions of dollars. Others are targeted at scientific applications rather than the office, while a third kind is just too difficult for the average person to use. But in my view, most importantly, most systems lack a programming interface upon which new or different applications can be built by third parties. In addition to meeting this complex requirement, a generally useful digital photography system needs to be inexpensive, simple to use, ubiquitous, and well integrated with the general information processing environment. This seems difficult to achieve, and if we attempt to provide a full range of photographic editing facilities, it clearly is. However, our study suggests that for many applications, a large proportion of the photo manipulation task can be accomplished with a relatively small set of well-chosen functions. In order to test this assumption, it seemed necessary to build and distribute an experimental prototype. It was hoped that experience with this prototype would shed light on both the user interface and architectural requirements, particularly those areas where hardware support would be appropriate. So, more formally, we set ourselves two project goals. First, identify a small set of image manipulation functions that are sufficiently powerful to meet most of the needs of Office users, yet remain simple to understand and easy to use. Second, implement those functions on a general-purpose workstation in a manner that encourages general use. In our environment, this means that ideally it should require no special hardware support. In short, we'd like to do for photography what the word processor did for document creation. This sort of system has come to be known as a digital darkroom. As we said earlier, our study suggests that users can accomplish a great deal with a small but powerful set of functions. There are 7 functions in our digital darkroom. The first is rather obvious. It's necessary to provide facilities for scanning images from a variety of sources, from paper, 35mm slides, or a video source, including the new medium of still video. On this digital darkroom package, images obtained from different media can be combined in a seamless manner. That's to say, combined so that you can't detect that they came from different media. The second function is at the other end of the production process, namely the ability to print. Transferring video images to a colour printer is both complex and expensive. Many new types of colour printers are emerging. For example, some thermal sublimation printers provide such excellent spatial and grey resolution that they outstrip the capabilities of the display. Clearly, it would be unfortunate if the digital darkroom constrained the quality of the output to the resolution of the display. For this reason, our system maintains image data at original scanned resolution and makes full use of this information during printing. Often this results in the printed image having more visible detail than the screen version. 4 editing functions can be distinguished that cut, paste, filter and geometrically transform images. Cutting out images is typically a tedious, error-prone and often unsatisfactory task, which is particularly difficult on low-resolution images. Such images may afterwards exhibit fringe or halo artifacts. It's important to be able to extract the desired features of an image with the minimum amount of effort and with a natural-looking result. In the digital darkroom, the user roughly outlines the edges of an object to be cut out using a fat paintbrush. The automask function then estimates the exact position of the edge, removing background colour from transparent regions, unblending edges and restoring transparency. The complementary function to cut is called paste. It merges images together while performing the correct blending functions at the edges and transparent regions to achieve a result that is often undetectable. Scaling, rotating and stretching are the most important geometrical transformations, but more complicated distortions are surprisingly useful. Filters allow the user to make non-geometric transformations to images. Filters are attached to images and then their shape can be adjusted to confine their effect to appropriate regions of the underlying image. Several filters can be stacked on top of one another to produce more complex effects. Most filters have associated controls that can be manipulated to vary the effect the filter produces. One kind of filter adjusts colour characteristics. Most images require some adjustment to their colour balance to obtain satisfactory lightness, contrast, saturation and cast characteristics. This is particularly necessary when images are obtained from input devices with different sensing or sampling characteristics. In that case, some image components may need to be adjusted to bring them into conformity. Another desirable image filtering operation adjusts the resolution characteristics. If a high-resolution image and a low-resolution image are on the same page, the low-resolution image looks relatively blurry, and the high-resolution image looks sharper and therefore more focused or closer. This produces depth of field characteristics, which may or may not be desirable. Lastly, and perhaps most importantly, the system must support undo and redo. These two functions allow the user to correct mistakes easily and to experiment painlessly with design ideas. In conclusion, our digital darkroom provides support for a wide range of simple applications that are required to manipulate photographic material. The system is in an early stage of development, but results gained so far are encouraging and have led to proposals for several novel applications. It's clear that with even very limited functionality, a great deal can be achieved.